welcome to this special series of Research Matters podcast. In today's episode, I, Spoorthy Raman, will be talking to two distinguished mathematicians. One of them is Professor Siddhartha Mishra, Professor at the Department of Mathematics, ETH Zurich. Professor Mishra is an applied mathematician whose research areas include numerical analysis, computational fluid dynamics, computational astrophysics, modeling and simulation of biological systems, and scientific computing. His work on differential equations has applications in broad areas, which he will talk about, and he is a recipient of many international awards and accolades. Professor Mishra is also the winner of the 2019 Infosys Prize in the Mathematical Sciences category. Professor Mishra, congratulations and welcome to this episode of Research Matter podcast. We are very glad to have you here.
Thank you.
The other guest with me is Professor Srinivasa Varadhan. He is a professor of mathematics and Frank J. Gaul Professor of Science at the Courant Institute of Mathematical Sciences, New York University, USA. He has been recognized for his contributions to the field of mathematics by various honors, including the National Medal of Science in the US and the Padma Bhushan from the Government of India. Professor Varadhan is also the jury chair of Infosys Prize in the Mathematical Sciences category. Professor Varadhan, welcome to this episode of Research Matters.
Thank you.
We are very happy to have you here as well. So, I will begin this episode with a question to Professor Varadhan. Still, mathematics is a field of science which is very abstract, and there is nothing much to touch and feel. Pretty much what we see around is in form of numbers, and that's what we as lay people are used to looking at mathematics. So, given this, unlike biology or chemistry where I can touch and feel, how is it that mathematics is able to touch our lives? What is your view on that?
Mathematics requires abstraction to some sense. So there are a lot of things that are happening in the real world, and one way to understand them is to unify them in some sense, have one explanation for many, many things. That's what mathematics achieves.
Mm-hmm. Thank you, sir. And do you have any comments on how we can see the impacts of mathematics around us in today's lives?
Everything you do today depends on mathematics. You take a plane to go somewhere, the wings of the plane have to be defined perfectly.
Mm-hmm.
The design of those wings depends on mathematical calculations that he does.
Right.
In the old days, people used to have wind tunnels, and engineers used to work hard to see how to design these things. Now you don't use wind tunnels. Instead, mathematics solves the problem.
Mm-hmm. Mm-hmm. Thank you, sir. Thank you for that opening. And my next question is, with this in context in mind, is for Professor Mishra. And like Professor Varadhan just mentioned, your mathematics seems to have, solving some of the cutting-edge problems that we see in today's world. So, can you give us a broader context of where your research fits in, and what are the broader areas of research that you're right now working on?
As Professor Varadhan so nicely explained, mathematics tries to unify things, unify physical phenomena, biological phenomena, things that happen in the real world. Many of these things are expressible in terms of mathematical objects, which are called partial differential equations. And the sort of core of my research is in partial differential equations, particularly nonlinear partial differential equations. The point about partial differential equations is that you cannot just sit down and write a formula to solve them, to find the solution. You have to approximate them, and you have to discretize them, solve them on a computer. That requires algorithms or numerical methods. And what I do at a fundamental level is design numerical methods, design algorithms to sort of approximate or simulate these partial differential equations, understand these algorithms, analyze them, implement them, and then work with other scientists, physicists, engineers, biologists, to apply these algorithms in the real world.
Mm-hmm.
So that's in a nutshell what I do.
And I think you touched upon partial differential equations as being the core of what you do in terms of mathematics. Could you help us understand, one, what is partial about these equations? And the second thing is about, some of the applications that we can relate to in this real world, which have basically stemmed from partial differential equations.
Yes, so what is a differential equation first, right? So you take a ball or a stone and you throw it. So when you throw it, the interest that you have is in calculating, for instance, how far it goes, right? And how far it goes depends how it goes, what's the path, what's the trajectory, right? And that is its position over time. So now to describe the position over time is a mathematical quantity, it's a function, it's coordinates, you can see that. And then to calculate that you use Newton's laws. So you find that the time derivative of position, that differentiation time derivative of position, the rate of change with respect to time is the velocity of the position. So this is an ordinary differential equation because this is only one derivative. But now you want to measure, for instance, the pressure of air in this room while I'm talking, right? So the pressure of air in this room while I'm talking is different when I'm talking because I'm changing air around me than when you look at the window there. While at the same time it's also different in time because when I stop talking, nothing happens. When I stop, it happens. So it's a function of various things. It's a function of position where I'm sitting and it's a function of time. So now, to calculate the pressure, the evolution of pressure, you have to see how the rate of change with respect to time is, what the rate of change with respect to position is. Now, these derivatives are partial because it's partial with respect to time, it's partial with respect to space. That is the partial in the partial differential equations because it's a function of many variables. Okay, so this was the first question, what is the partial in partial differential equations? The second question is why, it was about what kind of partial differential equations?
What kind of applications do these partial differential equations have that we see around us?
Just now I told you one example of that, right? So if you want to calculate the intensity of my voice, you can of course go and record it, or you can just write down a partial differential equation that perfectly describes it, or the noise that comes out from the traffic.
Right.
This is just a wave equation. Or as Professor Varadhan said, when a plane is flying, the air around the plane, it follows a partial differential equation called Euler's equations or Navier-Stokes equations. Or the temperature in this room follows a partial differential equation called the heat equation. So if there's a fire, the fire will spread, the temperature is going to change. This can be modeled with the heat equation. So you tell me what phenomena you're interested in, and I'll tell you what partial differential equation it satisfies.
Wow.
So they're everywhere. Wherever you look around you, there are partial differential equations.
Thank you, sir. That was really interesting to know, what kind of applications they have.
So anything, blood flow to your brain or growth of cancer in your cells, all of these are partial differential equations.
Anything that changes with
Anything that changes with time and space.
Right. So thank you, sir. Thank you for that wonderful explanation. And now on to Professor Varadhan. So we've heard from Professor Mishra about the range of applications that we just spoke about. You also added or gave us an introduction of what kind of calculations he is busy with and stuff like that. So as a member of the jury, when you decided to award him, what are your considerations on the influence of his work that has had on the field of mathematical sciences?
We look at the range of work, the quality of the work, in order to decide the winner of the prize. And we have a group of candidates who are all very good and who are all excellent. And then we have to make a decision. And the decision depends on many things, in particular, what is the field the candidate is working on. It's applied mathematics. And the question is, what kind of applications does his work impinge on? We find that he has a broad range of interests and his work is exceptionally good and it impacts many areas. And not only horizontally, even vertically, he does many things that needed to be done in order to complete the work. So I decided he was the best candidate this time around.
Okay, thank you. And coming back to you, Professor Mishra, you did say, okay, whatever we look around, you can design equations for us, which can help us understand and solve things better. What about things like societies and things that are not too quantitative in that aspect, but more in terms of quality in human societies, animal societies? Does this field of mathematics have implications for entities like this?
So, if you talk about social behavior, yes and no. Means but there we are on much more shaky ground in a way, right? Because the point about the physical world is that we understand the physics, right? To some extent, at least, we understand the physics, and once we understand the physics, we can codify them or encode them in terms of laws which have a mathematical foundation, which have a mathematical basis. If you talk in terms of social interactions, biology is also fine, because biology is physics. Biological systems are nothing but physical systems. So we can certainly apply the same principles. The physics is less well known, or the biological rules are less well known, but in principle this will happen one day. But if you talk like social interaction, people are doing that. They try to emulate what we have done for hundreds of years in physics, to describe the behavior of social interactions. For instance, some of my colleagues, I personally don't work on it, but many of my colleagues all over the world, there are subjects like social dynamics, for instance. What shapes opinion? What shapes consensus? How people make choices? These are governed, they formulate laws which take, for instance, the form of partial differential equations. So similar principles apply certainly to animal societies. For instance, when you talk about schools of fish, or flocks of birds, or swarms of insects, to describe these at some level, you can use the same principles as you do for the real world. So indeed, there are partial differential equations underlying it. There the physics is, or the rules are less well established, right?
Right.
So the validity of this has to be taken in a much more nuanced manner. It's unclear, at least to me personally, if the same approach that has worked so well for physics works also for economics or society, how people think. So this is, but it is done. It is done, not by me personally, but
Sure.
I certainly know people very well who do it.
Thank you, sir. The other thing that you did mention is about how do you codify things, and I'm assuming by meaning that you also talk about building models, that we are quite, use the word model in a very abstract way, saying, okay, somebody's built a model for explaining X, Y, Z. So coming to that particular question on model, as a mathematician, what in your view is a model, and what really goes behind in developing, what are small tenets that you look at behind developing a model?
A model has to be described in mathematical terms, right? This is sort of a basic requirement, a basic postulate. And actually, the laws of physics, I just gave you an example, right? Just about my speech, my talk, right? That when I talk, I disturb the air, and change the air pressure. This is very well described. This is very well modeled. I don't have to do it. This was done by Newton or Euler or someone long time back. So the systems that need to be modeled are more contemporary, like biological systems or social systems and so on. The point is, it's about rate of change, what are the factors that come in, and how we use. Each model has to have several building blocks, right? So what are the building blocks in the model? What are the basic mathematical structures that describe them? And then you put them together. So a model can involve partial differential equations, it can involve noise, stochastic effects, it can involve constraints. So it's there's no particular algorithm for designing a model. It has to be done contextually. And in many cases, the models are actually rather well known. What is unknown to us is how to solve them. That is the issue. Certainly in physics, right? Because in physics, we have understood physics for a long time, so many issues are well known. The implications of the model, how to solve them, what are the implications, this is what is sometimes unknown. in social sciences, is you have to do more modeling. You need to know something about the system. And I must confess that whenever I have modeled some things from the ab initio, from the very beginning, but I have not done it by myself alone. I have sat with a biologist or a group of biologists, and together we have built up something. But most of the models that I work on are very well established. They have been known for a while.
Thank you. And talking about some of the biological systems where you said you do sit with people who study biology as a discipline and then develop models. Could you give some examples of how mathematics is in the brink of influencing biology and helping us understand what we know as a separate field of this science to make things more clearer for, say, doctors or medical practitioners, things like that? What is your take on that?
It's an interesting question. My wife is a medical doctor, so I don't think I have been able to influence her much mathematically. But see, the let's say proliferation of mathematical ideas into biology is certainly slower than it is in physics or engineering, for that matter. It's slower, but it's happening at a constant pace now. And I have had some projects where we model things. I don't do it by myself, of course. I work with groups of biologists and doctors. For instance, a problem that we're looking at today is the problem is at an abstract level to build up a model for how the stomach functions. But at a concrete level, there is something called bariatric surgery, which is actually very popular in Bangalore, of all places. As a control mechanism for diabetes, right? And you do a bariatric surgery. So essentially what you do is you make a cut in the stomach, constrain the stomach somehow. But then the point is that the biological systems are meant to be robust, so the stomach starts regrowing, and in fact sometimes the capacity grows even bigger. So what are the control mechanisms for this, right? What are the biological control mechanisms at a cellular and molecular level? So what I work with my colleagues in Israel is to understand this process. So what we do is we have built up a simple mathematical model. It does not take into account all the complexities of the stomach. We test essentially the carrying capacity of the stomach, and then we do that pre-surgery and post-surgery. And we are able to observe many of the things that they see in the medical data. And then the question is controls, right? What are the systems that we are going to build on top of it to not let this happen, to let bariatric surgery work? So this is just an example. And the point about biological systems is that they're very complicated.
Right.
There are many players, there are multiple scales, so many interactions. And but this how it was also like this in physics 300, 400 years back, right? And then Newton came, and then there was, mechanics came about, and then we had electromagnetics, then we had relativity, quantum physics. I'm sure similar things will happen with biology also. It's just a matter of time.
And how do you think this is going to help surgeons who are doing bariatric surgery? To come back to your example,
it don't necessarily help surgeons. It will help. Maybe you need. So, for instance, there's a company in Singapore which makes a pill which is supposed to do the same effect as that of a bariatric surgery without doing the surgery. Right? So a surgeon is not going to benefit, but maybe we have a non-surgical, non-invasive procedure to do that. So these potentially, I don't know, I'm not a doctor, so I don't know that. I'm interested in at least modeling that and understanding what comes out of the model. I can't I can't do a bariatric surgery to say the least.
I prescribe pills.
Thank you, sir. That was an interesting example that you took of, considering that surgery is so popular, as you mentioned. So, sir, the question to you, Professor Varadhan, now is, as he gave an example, we are in this a nice crossroads between biology and mathematics. You, as a mathematician who has worked for a long time in this field. What are your thoughts about how mathematics is kind of charting the course for biology in that sense?
I think in terms of genetics, the origins of genetics are mathematical in nature, and various ways of identifying what part of the entire sequence is relevant for what is very statistical in nature. And probability theory, which is a part of mathematics, is used considerably there. So I would say it's discrete mathematics that I am familiar with that plays a role. He mentioned some examples of continuous mathematics, but there is also, see, in some sense, if you take a discrete problem and if the size becomes very large, then you approximate it by a continuous one. And if you have a continuous one and you want to solve it, you approximate it by a discrete one. So they are both two sides of the same coin.
Right. So have you had any experiences where there is this switching between?
Yes, because I do that. This is the whole point. Right?
Switching goes.
So I take a continuous problem and I discretize it. But when we model, we also take a discrete problem and we take the limit. Means we are so this constant. This not all mathematics, but many fields of mathematics. This is constant. What he does, what I do, we constantly use these ideas, passing between the discrete and the continuous.
Right.
So it's a very common trick or strategy.
And one of the things when you mentioned about approximations and trying to look at bigger things or the complex things is the field of astrophysics. And I think, Professor Mishra, you've had quite a few work on computational astrophysics. And astrophysics is a branch of physics that has really inspired awe and wonder among a lot of people, because there is this huge galaxies and entities that are always these mysterious objects that are around us. So going back to your work on astrophysics, could you please let us know how PDEs, which are partial differential equations, are applied to the larger realm of astrophysics, and what kind of problems are we attempting to solve there?
PDEs are dime a dozen in astrophysics because it's physics, right? And as I told you, physics is. So it depends on, astrophysics has two, I would say three aspects to it. Observational astrophysics, which is still the core of it, and somehow you need to observe, measure things, and this is sort of should be driving it. There's theoretical astrophysics, which is an attempt to explain these observations. Build theories about why it happens, why does, for instance, why do we have matter in the universe, right? Or why is structure the way it is, or why do we have stars, for instance, or how are stars formed, or galaxies formed. And then we have more increasingly computational astrophysics. And the reason for this is the following. See, theoretical astrophysics, many of the models are very complicated PDEs, for instance in supernovas or in the sun or in galaxy formation, matter formation. And these PDEs you can't, again as I repeat myself, you can't solve them by hand.
Right.
So you have to approximate them, and to approximate them you have to use the computer to simulate them. So a big part of astrophysics today, theoretical astrophysics, is computational astrophysics. People are constantly developing codes. I myself have contributed to some codes, and they are calculating, for instance, what is the star formation rate, or what is the galaxy formation rate, or questions like that, or what should be the temperature, and so on. So, a big field now is exoplanets. I have worked a bit on that. So, what is going to be the radiative profile of an exoplanet given so and so conditions? And then they match the observations, or based on the observations, they make some inferences about what sort of atmospheric conditions are there in the exoplanet. So, this is sort of a very well, let's say, modularized or well-developed concept in astrophysics. All of astrophysics is permeated by that. In particular, I am interested, I have worked on problems in solar physics, and I've worked on supernovas quite a bit. And as I said, the equations are the same. So I look at the equations, and of course the boundary conditions can be different, the scales can be different, the parameters can be different. But to me, it is not, and new issues come up. For instance, when you go from the sun to a supernova,
Right.
the temperatures are very different, the magnetic field intensities are very different, the dynamic behavior is very different. So you have to adjust a few things. But to me, the equations are fundamental, the PDEs are fundamental. And so we work on that, and we also work on very, very basic problems. Now, for instance, I've been working with people in GR, in general relativity, and they are very interested in black holes these days, and gravitational waves and things like that, binary black hole mergers, supernova induced gravitational waves, and so on. And they need a lot of computational modeling to constrain the observations. Means they get a lot of data, but to understand it, they need a theoretical framework, and this is provided by computations, which is where my work essentially comes in.
And you also mentioned saying that in the past 200, 300 years, pretty much of what we see in physics right now were kind of, started with models that have been well established and things. Right now, when gravitational waves was first detected with the advances in technological instruments to do so, has that had any effect on your field of mathematics per se?
Not in what I do, but of course it has stirred a lot of research on mathematical questions about, on purely mathematical questions about stability of gravitational waves. About certainly on the computational front, it has. This is Kip Thorne, who got the Nobel Prize. He keeps on emphasizing this, that of course it was the instrument that really detected the gravitational waves. But a decisive advance was done computationally to constrain the observations, and this is a part that is not given enough credit. And I've heard Kip Thorne mention this in lectures, that and he himself has spent quite a bit of time trying to build up this sort of computational models for it. So in my own personal work, no, it doesn't have any impact. I work with people to improve the models. But of course, this is beautiful. But let me remind everyone that this was predicted by Einstein in his theory, so it's more 100 years old.
True.
And Einstein was an idiot, so there is a double connection. There's a double connection to that, right?
Yes, absolutely. And when you talked about computational, ability that we have today, and with more powerful machines coming in, and we're almost the edge of quantum computing, with Google claiming to have had a working quantum computer. So, how exciting is computational mathematics going forward with all these?
Well, I can only say very exciting because I'm a computational mathematician. No, it's extremely exciting, but one has to. In mathematics, our time scales are long, right? Because time scales are long, and we should keep that in mind. So, computational power is increasing, but more slowly than before. And what has been sort of again not given enough recognition is, not only has computational power increased considerably in the last 30 years, but the algorithms to be able to utilize that computational power have gotten much better also. And there is almost a quadratic, so computational power increases by x. The algorithm has also increased the speed of the algorithm also by x, so you get x squared, a quadratic effect. This has slowed down a bit now because the computational power is slowed down, and new algorithms, the low-hanging fruit has been taken, so it's difficult to. But there is a sea change now because, particularly with machine learning and artificial intelligence, we as computational mathematicians have to use this, not least because hardware is driven by the things that we compute on is changing all the time. So when I started as a graduate student, most of the computation, all the computation actually, was done on central processing unit, the CPU.
True.
But then when I finished my graduation, when I was a postdoc, slowly people were using graphics processors. Now graphics processors were used started for gaming, for visualization, right?
Absolutely.
No one at that time thought that they will be useful for computing, for general purpose computing. But today, in my group, almost all my PhD students are proficient programmers on graphics processing units. And the decisive gains in computing that, at least in my group, have come from on the hardware side from GPUs. Of course, they have also come from algorithms, but they have come from GPUs. With the same quadratic effect, we got a factor of 10 from the GPUs, a factor of 10 from the algorithm, together we got a factor of 100. But now, because of machine learning, Google certainly has announced it, and there will be chips that are hard-coded for machine learning. And my fear is, because of the use of big data and so on, that will be where bulk of the money is going to be spent in terms of the hardware platforms. And we have to be able to use that as mathematicians to predict the weather or to make climate models or design aircraft or whatever. And so we have to do this. And already in my research group for the last couple of years, we have started our first projects. I see a very promising future. Mathematicians are as usual are a bit slow in reacting, which is good because our time scales have to be conservative. But I think there is tremendous. The questions that come in are very exciting. So at the moment, almost half of my research group works on the connections between artificial intelligence, machine learning, and computational science, computational mathematics. You also asked a question about quantum computer. And I don't know much about it, but I know enough to say that Google made a claim, but it's still some ways from realization. But maybe it's faster than we think.
Okay.
Because 20 years ago, when I was a PhD student, this was science fiction.
Right.
Today, it's almost science. So I don't know. In 20 years, this could be. Maybe there are certain applications where this could provide massive breakthroughs. I don't see it yet, but I intend to think about it, certainly, and maybe. I also didn't see that machine learning would be useful 5 years back, but now I do see that it is useful.
Right, changing times and changing.
Yes, we have to be at the frontier. We have to incorporate what's going on, particularly because the hardware changes.
Absolutely.
And then we have to respond.
Yes, thank you for those insights, sir. Coming back to Professor Varadhan. So, in your view, what's the decade holding for the field of applied mathematics? What are some of things that you hope that this decade brings to the fore, or challenges?
You can never tell what the challenges of the future will be. So I'm sure there will be issues and problems raised in the future, whether it's global warming or whatever it is. And I feel that I hope that the mathematicians will be able to understand those problems and to devise methods for solving them, and then applied mathematicians can work together to solve these problems. So one can't tell what will happen until the problems are there.
Right. So these are the challenges that you hope that.
Depends on what comes up.
Right. Do you want to add something to this, Professor Mishra, considering we are in a challenging world anyway?
Yes, as Professor Varadhan said, who knows what the future holds for us, right? But as I said, many of these things, they also pose a very interesting set of purely mathematical questions. And I think again, this distinction between pure and applied mathematics is just semantics. We only have mathematics, and so the mathematical questions are already interesting. There are groups of mathematicians who try to even use tools like combinatorial topology to understand sort of the topology of neural networks. So people are doing that, and at the same time, we also have mathematical questions that are unresolved for 500 years.
Riemann hypothesis.
Yes, we have several questions that as I said, mathematics works at multiple time scales and very, very long time scales. We have questions that have not been resolved for 250 years, 300 years, 400 years.
For example, the equations that he is trying to solve, we are trying to show that the solution exists.
For 250 years now, and 275 years now. Okay. In fact, my talk tomorrow at the Tata Institute here will be on that. Means, as a mathematician, this is what drives me, that to just understand questions like that. So we operate at different time scales, and as a community, as mathematicians, we have been able to at least attempt to understand these questions rather quickly, and we take our own applications are faster when our own, our due diligence proofs and so on come later.
So it's a continuous, effort to solve long unsolved problems to one hand, and probably approach it in different ways that I would understand with different tools that are at your disposal at the moment compared to what you had 100 years ago, maybe. And
100 years, of course, we change.
So yeah, thank you so much, and I think we are towards the end of this whole podcast episode. We aim for usually 30 minutes is what we do. So thank you so much for your insights and sharing your experiences and anecdotes about your relationship with mathematics that you've had for so long. So thank you so much for that, and it was great having both of you as guests in today's episode of Research Matters podcast. So with that, I wish you all the success in the challenges that you were trying to solve, and Professor, you too in what the decade holds for mathematics that you pursue. Thank you both, and have a lovely day, both of you.
It's been a pleasure.
It has been our pleasure.